Okay, so we're online and okay. This work was done in collaboration with a number of people through discussions that extended over a couple of years, and it's coming or converging. But I think it's beginning to build a nice story that I would like to present during this time. The work was done in collaboration with Roderick, who's a long-standing friend, and also at Kent, Jorge Quintanilla and Claudio Marcello, who is now was a student at Kent, now is a postdoc in Grenoble, Saranko Balakrishnan and Vladimir Gaznesian at CUNY, and the involvement for numerical simulations of an undergraduate student at Stonybrook, Matthews. And as I said, it stretched through a number of years, and the idea progressed through discussions with many people, some of which in the audience, some of them in the audience, and others are not present, and I'm grateful to them and many others. So, overall, our work was under the umbrella of trying to understand dynamics in spin liquids, and even though I don't really need to introduce the topic to this type of audience, I want to maybe stress the importance of this and the fact, in some sense, witnessing the number of efforts that have been produced in recent years to understand these dynamics. It's interesting from a fundamental point of view. These unusual phases of matter are rather exotic in their behavior, and therefore it's meaningful to try and understand what response and relaxation properties may be. They have very unusual quasiparticles, so understanding their motion is very interesting. And recently, dynamics specifically, for instance, the dynamic structure factor, has proven rather important in detection and diagnostics of these phases. Understanding spin liquids, especially from a experimental point of view, is a rather arduous task. They are elusive phases of matter, and we need better signatures that are smoking guns, and some of them appear to be actually the dynamical properties. And in general, there are several other questions, speculation of topological states, thinking about how to operate in this space for information processing, quantum computing, and there are interesting connections with classiness and kinetically constrained models. Obviously, this is a very broad initiative, and the angle at which we came into is actually going and revisit the origin of the dynamics, and that's what stimulated the work we have done. If we look at what can give dynamics to this system, we have to contrast thermal versus quantum fluctuations, the interactions, the fact that the local crystallographic environments is very elaborate in many of these spin liquid candidate materials, and the role of the environment. And what we found is that, at least in some of these systems, there is an interesting interplay between local spin correlations and the transverse terms due to interactions acting on this isolated, so say at the local level of microscopic ion, that give rise to a potential correlation between the dynamics of these systems and the local spin correlations. And this is what I want to present in this talk, specifically focusing on a case in point, which is gyrospinized materials. But some of the arguments I present are hopefully applicable more generally to other candidate spin liquid materials. The source of dynamics that we will look at, which is not necessarily the only one in these systems, is that due to internal fields, meaning the very same interactions that lead to the spin liquid phases in the system lead to transverse that are kinetic in a quantum sense and lead to quantum fluctuations. The interplay between interactions and lattice geometry brings about what I just said, these very strong correlations between kinetics and the local spin structure surrounding a given ion that give rise to, in the case of spinized materials, gives rise to a bimodal distribution of transverse terms that you can look at as, say, tangent amplitudes or timescales. And so the way that a spin precesses under this transverse term, or its time scale, is strongly correlated with the local spin environment in a bimodal way. From this microscopic picture going towards a many-body effect, this suggests that at the level of classical spinize, perhaps a new paradigm is necessary in terms of describing these systems with stochastic dynamical simulations, where two timescales are present that are actually a mean that are determined by the spin structure itself. At the quantum spin level, well, it's much more difficult to make predictions, but we worked on some toy models for quantum spin ice that I will discuss, and it leads to some interesting new phenomena such as wave functions that have a fractal structure, near localization of their excitations, and calculations of monopole conductivity that can be actually compared to experiments, for instance, thinking about terahertz magnetization dynamics in these systems, which are already available and can be contrasted. And I come to the conclusions at the end. So the focus of the talk is rare earth, well, titanates really. Rare earth and metal oxides. I'm going to spin ice. I really don't need to introduce them to this audience. But the three key ingredients that I will be discussing are the fact that these are Pyrochlore systems with a strong crystal field anisotropy, so these are very polarized spins along the easy axis, and they have exchange and dipolar interactions that cannot be neglected. Combined together, these ingredients lead to a cohort of exciting thermodynamic behavior that are beyond the point of this talk, and I will not be discussing them at all. What I focus instead is the spin dynamics. And to understand it, we can actually take a step backwards in time, about 14, 15 years, and look at, for instance, what magnetic susceptibility tells us. From these measurements, it's possible to obtain, as Snyder collaborators did in 2004, a time scale as a function of temperature, which is indicated by these black crosses. And we see that there are essentially three regimes. At high temperature, there is a temperature-dependent regime. This is a log scale, this is linear. So linear behavior here is characteristics of activated behavior. Activated behavior that is well understood by the fact that you have, for every single ion, a local crystal environment given by the oxygens that introduces crystal field levels that we've heard about in earlier talks, and the energy levels that thermally populated at these temperatures, and that corresponds to the dependence we have here. To understand that phenomenon quite well is just thermal occupation of excited crystal field states. This behavior is then cut off by a regime that seems to be essentially temperature independent until at much lower temperatures the timescales start to grow again in a dramatic form. Whereas there are still maybe questions, subtle questions about this behavior at very low temperature, the leading order of it is well fitted by different theories shown here in various colors of symbols. And they are due to many body effects in the system, which is not what we are interested in this, in our study. What we are interested in is just the cutoff here. And if we could subtract off this many body behavior, what we would have is that this plateau would continue, at least to the best of our understanding to date, in a temperature-independent fashion. This suggests that in this system, this is dysprosium titanate incidentally, but behavior is very similar in many of the related compounds. What we have is that at low temperature, the thermally activated dynamics across energy levels in the crystal field is cut off by a temperature-independent timescale. And that is typically associated with quantum fluctuations or quantum tunneling processes, a quantum amplitude for flipping the spin. So we need to look for a reason, for a phenomenology that can explain this observation. And the route that we chose is actually to look at possible quantum fluctuations due to the transverse component of the interactions in this system. So we have a strong crystal electric field that makes these spins very easy-like in their behavior, even though they are large electronic spins, and we have dipolar exchange interactions with them here. And we need to put them together and try to figure out what is the role of the transverse component in this system. That's going to be the scope of the next couple of slides. I wrote here explicitly the dipolar interactions because everybody agrees on its form. The exchange I kept it symbolically for the time being because exchange interactions in these systems are very complicated. They've been written in many different ways throughout many years at different levels of approximation. And we look at them carefully one at a time. But the first thing I want to do is cut all of this to nearest stable level and use the simplest possible Hamiltonian that has been considered for spin ice, which is S.S Hamiltonian, just because it's easy and intuitive for what I want to say, not because I think it's realistic. So I will take the Hamiltonian nearest neighbor level S dot S, which means that for a single ion I, the action on that spin is actually due to a field that is the sum of the 6 neighbors shown here in the figure, S1 plus 6. Something fairly simple that is known oftentimes as the exchange field acting on the central spin I. If we take this configuration is one of the low energy states for spin ice, 2 into R for every tetrahedron at each of the 2 tetrahedra. And there is an easy way to look at the summation of the 6 spins by noting that the easy axis of 1 is the same as 4, 2 same as 5, 3 same as 6. So if 1 and 4 are pointing opposite to one another, they cancel. So that's 0. 2 and 5 are opposite to one another, that's 0. S3 and S6 are equal to one another, they are the only thing that acts here. And if you put them together and if you make them act on the central spin, what you see is that they do have a transverse component, but there is a long longitudinal component pointing along the direction or parallel to the direction of the arrow shown in the figure. This is not surprising, I'm just stating the obvious here. That is the ground state of spin ice, and therefore the local interaction are parallel to the way that the spins are pointing. That's the ground state. So we expect that the transverse component in this case at best will induce some precession, but will not lead to the flipping of the spin because the spin is happily sitting in the lowest energy state. What happens, however, if we have an excitation here in a setup where this excitation can move to the other tetrahedron at 0 energy cost? That's property typical of spin ice. Instead of moving the main balls, you move at point-like excitations. In this case, if you do the summation as you do the same trick as before, 2 and 5 cancel out, but 1 and 4 add up, 3 and 6 add up, and the resulting field is shown in the green arrow here. It has a finite length, and it's purely transverse. Again, it's consistent with our understanding of the dynamics of spin ice. There is no preferred direction for the spin in the center. There is a transverse field that can induce dynamics. So we have a potential source of quantum fluctuation in this system. Up to now, again, everything is trivial. But this is not the only configuration that is consistent for monopoles sitting here being able to hop up. What we can do is reverse the direction of 1 and 2 in this way. What happens is that the green resultant of these 6 spins is rotated, but is still purely transverse, and it's the same length as before. No surprise, we still have a source of dynamics. There is a third inequivalent configuration that occurs if you swap now S2 and S3, and that's what happens. There is no arrow for a good reason. 1 and 4 are opposite, 2 and 5 are opposite, 3 and 6 are opposite. There is no field whatsoever acting on the central spin. If I took this model face value, there would be no quantum fluctuations coming from the Hamiltonian. There is no energy term that would make this spin do anything whatsoever. There would be a zero acting on it. It would be static just by sheer non-interaction. And so we have the situation where the same domain rule hopping or quasi-particle hopping process can occur with a finite transverse term or zero, depending on the setup of the neighboring configurations. Neighboring spin configuration. This is an overly simplified Hamiltonian. What happens if we actually look at something more realistic? Let's start with bipolar fields. We can run Monte Carlo simulations and sample the local fields acting on a spin to all the other spins in the system. This is long-range bipolar. We get the same very much picture. Away from monopoles, this is the probability distribution of the parallel and perpendicular component of the field. There's a strong parallel component. Away from monopoles, the system is sitting in its low energy state. No surprises. Next to a monopole, the parallel component drops to 0. This is a zero energy move to leading order. And the transverse component is bimodally distributed, with one peak at finite value and one very close to 0. If we integrate out these two peaks separately, we get again a 2-to-1 ratio. So we get a very similar picture, just broadened as we expect by corrections due to long-range interactions in bipolar sense. So the picture remains very much valid if we go from the previous nearest neighbor term to full long-range bipolar interactions. What about exchange? Exchange are very peculiar, as we have seen in the systems we have seen in earlier talks. They can take on very anisotropic forms, and you can choose the level of approximation you want, but you can take it all the way to the most accurate calculation I'm aware of, which is going back to electrons and realizing that the interactions between two neighboring F moments is actually a 4 for the perturbation theory calculation of electron operators via the p orbitals of the intervening oxygen. This is a calculation that was done by Oda and Tanaka in 2011 for praseodymium. You extend it to states, the ions that have many more electrons, and it gets into a fairly ugly calculation, but it's doable. I mean, the details are completely irrelevant. The point is that you can work out the full FF electron interaction, write it in the J and J total angular momentum basis, and then we can look at the exchange Hamiltonian on spin I, which is the sum of the 6 nearest neighbor coupling between I and J, J being the 6 neighbors of given site. Now we have a multi-spin Hamiltonian operator, so we need to decide what to do, and it's not immediately easy to interpret it as a field. So in order to understand what it can be in terms of an transverse component, we need to make an approximation. The working assumption we have done is to do the following. For each of the 3 inequivalent configurations we consider here, we take this many-body operator and we project it on the ground states of the 6 neighboring spins that correspond to the arrows depicted in this figure. Now, many of you can tell me that's wrong. Some of them are as dynamical as the central one. Yes, we can discuss it later happily, but this is the only working assumption I know how to go forward with, so that's what we decided to do, as at least an informative point of view. And then if someone has a better idea of what else can be done, I'll be happy to hear it. But thanks to this projection, what we can have now is a new projected exchange term on this ion I, which is a single ion operator again, in the full J and J basis, so it's still a, well, for dysprosium would be a 16 by 16 Hamiltonian, and fairly large object. Again, we cannot interpret it really as a field, but we can do something. We have 3 cases. We can add it to the crystal field interaction and see how, so crystal fields imply Hamiltonian and see how it behaves. And what is surprising is that in this case, again, we find that that operator has no transverse terms by symmetry. Or equivalently stated, if you combine it, this Hamiltonian H exchange plus the crystal field, there is no splitting of the ground state doublet in this case, whereas there is a splitting of these 2 cases, and the splitting is the same magnitude. So again, we have the same 2-to-1 dependence, even though now we lose the ability to interpret it naively as the vector summing to 0. But we have the 2-to-1 dependence on the local spin correlation, where we have a splitting, therefore dynamics in 2 of the cases, and finite splitting and 0 splitting in the 3rd one. Okay? We can then put everything together a bit more concretely and look at, for instance, time scales by looking at all the terms we have acting on the central spin, which is the crystal electric field Hamiltonian, the bipolar terms, and the exchange. We can initialize the central spin to a given state and see how it evolves in time. And what we find indeed is that the ground state wave function, the wave function of this spin undergoes a quantum mechanical precession where weight is shifted from the spin pointing in one direction to the other and back with a characteristic time scale that we can obtain. It corresponds to the splitting energy levels that we would expect. And for dysprosium and holmium titanate, what we find is that the fast time scale, remember these 2 cases here, we have order of microseconds, and for the slow time, wrong direction. For the slow time scale, we get about a millisecond. The values are eminently sensible for these systems compared to experiments in existence equilibrium USR. However, I wouldn't necessarily rely on the actual numbers or that you find there too much, so I still would like to understand their accuracy, but I think that the splitting in time scales is an important phenomenon, and even if we were to model this classical spinices, perhaps a new paradigm is needed in the stochastical dynamical simulations for this system that introduce 2 different time scales with three orders of magnitude difference between them in how quickly a spin flips, depending on the local spin correlations. This is in principle an easy thing to check, but we haven't got around to doing it yet, so it's still a question mark how much of a difference it makes to stochastic dynamical simulations of this system. What's interesting, instead perhaps even more interesting, is the case of resolinium steinate and resolinium zirconate, typical examples of candidate quantum spin-ice materials, where the different separation of timescales is becoming ludicrous, in the sense that the fast one are 10 picoseconds, and the slow one is 0.1 microseconds. This paints a very important picture now, because if you think about the chances of having quantum mechanical coherent processes, 10 picoseconds is realistic in a magnet, 0.1 milliseconds is not going to happen. So it suggests that actually, in quantum spin-ice, perhaps one can divide this timescales and treat in a Born-Oppenheimer way the fast timescales as a quantum hopping process that is finding its ground state, whereas the other one is a stochastic event that happens from now and then in incoherent manner. So very briefly, what we did at the many-body level, so far all of this is a single line picture. What can we learn at the many-body level? We took quantum spin-ice one dimension down for simplicity to square ice. We can still define rules in a way that flipping a spin that transfers an excitation can be a slow or fast process, and work in a number of approximations of dilute monopoles, so isolated monopole limit. We ignore ring exchange processes, so the dynamics is only due to monopoles, and we work in this Born-Oppenheimer approximation, where essentially the slow tunneling amplitude is negligible with respect to the fast one that happens coherently. And what is nice is that now we can use effectively the spin-ice configurations as stochastic sampling over networks, where we do diagonalization for the excitation hopping processes. We can find the density of states of action of energy, look at the wave function, find actually inverse participation ratio, and we find signature of non-ergodic behavior on the wave function and monopole localization. If I could abuse the time for one more minute, there is something I want to say more. Monopole up is essentially spin flipped, which is ionization dynamics. And means that all of these predictions can be used to turn into monopole conductivity type calculations that can be related to, for instance, ultra-fast magnetization measurements that have already been done in the literature. They were done for a turbine titanate, and I'm not making the case here that the turbine titanate is, or is not a candidate quantum spin liquid. Perhaps the quantum spin-ice, perhaps the evidence nowadays is more that it isn't. But nonetheless, let alone the experimental data here, what's interesting is that the measurement that were done by the group of Armitage and collaborators can allow to obtain the real and the imaginary part of the conductivity, and they were related to theoretical calculations that are the solid lines here, where the authors claimed that they had to extend the classical hydrodynamics for monopole excitations in spin-ice to a model that includes band mass for them, and that was the necessity to explain a negative dip in the imaginary part. And the point that I want to bring home in our calculations is that actually, using the localization phenomenology that we have, we can compute the current matrix elements in real space and obtain real and imaginary part of the conductivity. And again, this dip shows up in negative part, which is a diagnostic of near localization, and in this case, not due to a band mass. So the take-home message is that you can actually explain a dip here in negative from two possible origins, band mass or localization. And so it's not necessarily only band mass that can give that type of feature. I leave the conclusions up, I think, the German standing, and take any questions. Thank you very much. Thank you.
So, we have time for a few comments or questions. Who's the first? Everything pretty clear? So,
not at all.
No. Peter?
So sorry, I might have missed the detail of how thinking about the own job of the football. So in disposing titanate, the fast and the slow time scale. So the millisecond time scale, is it coming out of your calculation or not?
Yes. So we have three configurations locally. This one would be completely static from a point of view of exchange only, but it acquires a non-zero transverse component of the field due to dipolar interactions. So when we did the calculations, we put together, like, as I said, dipolar, exchange, and crystal field. So the time scale here would have been infinity if we only had crystal field plus exchange, but because we also have dipolar, it's not infinity, it's actually 1 millisecond. So the dipolar corrections are there.
Okay.
So my understanding of the history of dispersion technique is that it has been well studied in the field of classical spin ice material, and there may be quantum spin ice dynamics that could theoretically be explored. So I wonder if there is something that would cause dispersion technique to choose the state with that field excitations with those two three possible states, or versus that ground state, which would be the classical spinors.
So maybe I should just comment here to try and clarify. Maybe I don't do it very correctly. In the case of classical spin ices, we still have this behavior where the thermally excited reversing of a spin is truncated by a temperature-independent process. So even in classical spin ices, we have to invoke quantum tunneling to explain this. At least, to the best of my understanding, we don't have another way of explaining it. Maybe someone has, and I'm happy to hear it. So the case I have in mind for these systems is that there is a quantum tunneling process that reverses a spin, but between multiple processes, the coherence is lost altogether. And therefore, there's no quantum mechanics in spin ice, no quantum selection of ground states. But the dynamical event of a single spin reversal is quantum mechanical in nature.
There have been several recent measurements of homing and dysprosium tightening looking at magnetization relaxation measurements that have shown timescales on the order of days. Have you thought about tying some of these slow dynamics to the relaxation curves that some people have published in magnetization?
Yes, but I haven't done anything yet in that direction. I'm curious. I suspect that the difference in these timescales that comes from this talk will introduce a quantitative difference, but not of that level, not a qualitative change in behavior. So it could lead to a better fit of, say, classical stochastic Monte Carlo and used as a dynamic assimilator for these systems to exist susceptibility measurements, but it would be a parametric adjustment in the sense that you are still at two timescales with 3 orders of magnitude difference between them. I don't expect that to lead to a dramatic change. But for instance, one place where it could make a difference is that in the many-body agreement, so in the agreement between the many-body divergence here of timescales and experiments, maybe these two timescales could make a difference parametrically.
So I have a question about localization. Can you say something more about the origin of this localization picture that you mentioned?
So effectively, for every multiple excitations you have in spin ice, there are 4 directions it can move, whether you're in square ice or on real variable, it's the same. One is completely forbidden because hopping through that will generate double monopoles, so it's up in energy. Of the 3 remaining, the picture we have is that stochastically, 2 of them are fast and 1 is slow. And slow in quantum spin ices means really it's not going to happen. So it means that all of a sudden spin ices are moving on a very sparse network because it's a network that had original connectivity 4, 1 is forbidden. In fact, deflective connectivity is actually 2 on average. There will be a lot of dead ends and a few branching points. That is what leads to localization. This order of delocalization, in fact, matter of fact, generated by the spin configuration.
So I had a quick comment on the previous question about the very small relaxation dynamics, which is completely dependent on the power of the body itself. So the one-inch dipole interactions favor chain-based states and the spinized configurations. This is an effect that can be shown in defrustration. And then you need to move your monopole, basically macroscopic distance, which is not equilibrium chains. So regardless of what your time scale is, your simple scale is
I was going to ask if you anticipated any difference between, say, holmium technique and dysprosium technique, these dynamics on the virtue of one being progress and the other being non-progress. And is this phenomenology observed in both cases?
The answer to the second question is easier, I don't know. The answer to the first question, yes, there is a whole other section of dynamics that is possible in the systems for the non-Carnot space that has been studied by several people here, which we have not considered. Putting the two together would be interesting, but yet another level of complication. But yeah, so the reference that in non-Carnot ion, then the possibly local distortion or anyway structural change in the material can lead to a splitting of the ground state doublet in the crystal field that is equivalent to a transverse component in the quantum Hamiltonian, if you want. But this we have not included in our considerations. Yes.
Okay. So, thank you, Claudio, once more.
Thank you.
And we move on to the last talk of this session by Peter Holzberg, multiple monopole phase transitions in spin ice.